For all things health and fitness, this is the Army Gymnastics Podcast.
The Army Gymnastics Podcast.
Discover a fitter, healthier you at ArmyGymnastics.com.
Welcome back, everyone, to the Deep Dive. Today we're tackling a really important topic, aggressive prostate cancer. It's a complex area, Treatments have come a long way, but these aggressive forms, especially the ones that learn to resist standard therapy, they're still a huge hurdle. A lot of treatments focus on the androgen receptor, the AR pathway, but the cancer cells, well, they get smart. They find ways around it, and that's often when things become really dangerous. So understanding how that resistance happens and why, it's absolutely critical.
It really is. It's sort of the central problem, isn't it? In advanced prostate cancer, we often do okay with early stage disease, but when it turns aggressive, when it becomes resistant, that's where we really need better answers. It forces us to dig deeper, beyond the surface level treatments and understand the fundamental biology.
And that's exactly what we're going to do today. You've brought in some fascinating source material that looks at this from, several different angles. We've got a consensus statement from medical experts, really practical stuff about how genetic testing is being used right now in the clinic. Then there's a deep dive into the lab work, a research paper looking at how these cancer cells fuel themselves, their metabolism, and how that ties into treatment resistance. And finally, a news piece about a newly identified gene that seems to be a key player in how cancer cells actually, change their identity to dodge treatment.
Yeah.
Pretty amazing stuff.
Yeah, so we're getting the whole picture, hopefully, what doctors are grappling with today, using genetics to make better decisions, and then what the researchers are uncovering in the lab about the cancer's, let's say, survival toolkit, its energy sources, its ability to shapeshift.
Exactly. So our mission is to pull out the key insights from all of this, help you get up to speed quickly on where things stand and where they might be heading with aggressive prostate cancer. Okay, let's get into it.
Right. Let's start with the clinical side, where things directly impact patients. This consensus statement on genetic testing, it's really about how doctors are using genetic information today to better handle aggressive prostate cancer.
And it makes a key point right away. Prostate cancer isn't just a problem in, say, North America or Europe. The incidence is climbing fast globally. This source specifically mentions a rapid rise in Asia, like in Hong Kong, where these experts convened. Traditionally, doctors relied on staging, PSA, Gleason score, the usual metrics. But this statement really emphasizes that genetic testing is becoming, essential. It's not just an add-on anymore.
That's the core message. The genetics of prostate cancer, especially when it's advanced, they tell a story. They reveal specific vulnerabilities, potential drug targets. The source actually quantifies that something like 11.8% of men with metastatic prostate cancer have inherited mutations in DNA repair genes. That's quite a bit higher than in localized disease. And if you look at tumor tissue itself, somatic testing, in castration-resistant prostate cancer, maybe around 23% show these clinically relevant DNA repair pathway changes. These aren't just random variations. They're changes that seem to directly influence how the cancer behaves, how aggressive it is, and how it might respond to certain drugs.
So finding these genetic changes isn't just interesting information, it actually guides treatment.
Precisely. That's the whole point. Identifying these specific mutations, whether inherited or acquired in the tumor, can flag patients who could benefit from targeted therapies. Therapies designed to exploit those exact genetic weaknesses. It's a real shift towards personalized medicine. It's happening now in prostate cancer.
Okay, so if it's that important, who actually needs to get this testing? And when? The consensus statement seems pretty specific on this.
It is, yeah. And it actually starts even before someone is diagnosed. For anyone newly diagnosed, the first thing is a really thorough family history. And we're not just talking about dad or grandpa having prostate cancer, it's broader. Looking for patterns, breast cancer, ovarian, pancreatic, even colorectal cancer in the family.
Right, they have specific criteria, don't they? Things that should really trigger more investigation.
Yes, exactly. Like having a close male relative, father or brother, diagnosed young, say under 60, or dying from it young, or multiple relatives on one side of the family with prostate cancer, or those other related cancers we mentioned. And of course, if someone in the family is already known to carry a specific mutation, like in BRCA1 or BRCA2 or Lynch syndrome genes, that's a major red flag.
So that family history is like the first net, the initial screen.
It is. And if that history is concerning, or if there's a known mutation in the family, the consensus says you need to talk to healthy family members who might carry that same mutation. discuss surveillance options, maybe preventative steps. They specifically call out BRCA2 carriers, suggesting they might need to start prostate cancer screening way earlier, maybe age 40, or even 10 years before the youngest family member got diagnosed.
Wow. So thinking about screening differently for people without cancer, just based on their inherited risk. That's powerful. What about for someone who already has the diagnosis?
Okay, so if someone is diagnosed, the consensus recommends considering germline testing, that's testing for inherited mutations from blood or saliva right away if they present with metastatic disease.
Because the mutation rates are higher then.
Yeah, significantly higher. Also, if the pathology report shows certain aggressive features like ductal or intraductal histology, those are linked more often to inherited mutations. And obviously, if that detailed family history we talked about is positive, those are the main triggers for germline testing at diagnosis.
Got it. Metastatic disease, aggressive subtypes, or family history. Makes sense.
But where genetic testing really changes the game right now in terms of choosing systemic treatments is in metastatic castration-resistant prostate cancer, MCRPC. Here, the consensus is crystal clear. All patients with MCRPC should be tested for actionable genetic mutations.
All of them. Okay.
All of them. And for this group, somatic testing the tumor tissue itself is usually the first step.
Why somatic first in MCRPC?
Because it gives you the highest chance of finding the specific mutations in the tumor that's currently growing and resisting treatment. Those are the mutations most likely to be targetable with therapies available today. You want to know what's driving that specific cancer's resistance.
Okay, that logic tracks. Test the active enemy. But you mentioned confirming with germline testing sometimes.
Yes, that's a really important point. If the somatic tumor test finds a mutation in a gene we know can be inherited, think BRCA1, BRCA2, ATM, the mismatch repair genes, then it's really crucial to check if that same mutation is in the patient's germline DNA too, usually from a blood test.
Why is that double check so vital?
Because finding it in the germline confirms it's inherited. That has huge implications, not just potentially for the patient's own treatment options, but critically for their blood relatives. It means family members might also carry that risk and need counseling and potentially screening.
Right, that cascade testing for the family sounds complex.
Yeah.
What about the practicalities of getting the testing done? Any technical hurdles?
The source mentions a couple of things. One is detecting what are called large genomic rearrangements, or LGRs.
LGRs.
Yeah, basically big chunks of DNA missing or duplicated within a gene or chromosome. Standard somatic testing methods, like next-gen sequencing or NGS, sometimes struggle to reliably pick these up. So if a patient has a really strong family history suggesting an inherited syndrome, but the standard somatic test is negative, you might still consider doing a germline test from blood, as some methods used for germline testing are better at finding these large structural changes.
Interesting. So the type of test matters. What about the sample itself? Where does the tissue come from for somatic testing?
Usually it's from formalin-fixed, paraffin-embedded tissue, FFPE. That's the standard way biopsy or surgery samples are preserved.
So tissue from a previous procedure.
Right. But the consensus notes there can be issues. You need enough tumor cells in the sample, the quality has to be good, and sometimes how long it's been stored can affect whether you can get a reliable result. A pathologist needs to review it first.
And then there's liquid biopsy. That sounds less invasive.
It is. Liquid biopsy is analyzing circulating tumor DNA, or ctDNA, tiny bits of DNA shed by the tumor into the bloodstream. It's becoming a really practical alternative, especially when getting a new tissue biopsy is risky or difficult.
Like if the cancer is spread mainly to the bones.
Exactly. Bone biopsies can be tricky. Or if the patient isn't well enough for a procedure, a blood draw is much simpler.
And you can learn the tumor's genetics from that.
Potentially, yes. It can pick up key mutations that might predict treatment response. Some research even suggests you could monitor how well treatment is working by tracking changes in ctDNA over time. Generally, the more cancer someone has, the more ctDNA is shed, so the better the chance of getting a useful result from a liquid biopsy.
That's really quite something. Okay, so when they do these tests, are they looking at just BRCA1 and 2 or more?
Oh, much more, especially for metastatic disease. They recommend using multi-gene NGS panels. These panels cover a whole suite of genes known to be involved in prostate cancer progression and potentially targetable.
What kind of genes are we talking about?
Definitely the DNA repair genes, the homologous recombination repair ones like BRCA1, BRCA2, ATM, PALB2, CHEK2, and others. Also, the mismatch repair or MMR genes like NLH1, MSH2, MSH6, PMS2, which are linked to Lynch syndrome. But the panels often include other pathways too, like the PI3K pathway, RAS-RAF-MEK, genes frequently altered in advanced cancer. And they might look at genes like HOXB13, linked to inherited prostate cancer risk, or TP53, a major tumor suppressor, and CDK12, another DNA damage response gene. It's quite comprehensive.
You mentioned mismatch repair genes. Does that connect to immunotherapy?
Yes, it does. Those MMR genes are linked to a biomarker called microsatellite instability, or MSI. If a tumor is MSI high or deficient in mismatch repair, dMMR, it tends to have many mutations, which can make it more visible to the immune system. And these panels often assess MSI status along with tumor mutational burden, TMB, another measure of mutation load and PD-L1 expression. These can help predict who might benefit from immune checkpoint inhibitors, ICIs, like pembrolizumab.
Right. Pembrolizumab has that approval for any MSI high cancer, doesn't it?
Exactly. It's eye-agnostic. So if a prostate cancer patient's tumor is MSI high or dMMR, pembrolizumab is a potential treatment option based on that genetic finding.
But the source mentioned something about MSI and prostate cancer specifically.
Yeah, a bit of nuance there. While it's relevant, MSI high status is actually pretty rare in prostate cancer, maybe only around 3% of cases. So it's important, but applies to a smaller group. They also note that TMB can be high sometimes, but it doesn't always track perfectly with MSI status in prostate cancer. And because MSI is rare, they recommend using NGS-based methods to test for it, as other methods might not be sensitive enough.
Okay, so these comprehensive panels give a detailed genetic snapshot. Now, the crucial part, how does this actually change treatment? Let's walk through the different stages.
Right, this is where it gets very practical.
What about localized disease? Cancer's still just in the prostate.
Here, the biggest impact of germline genetic testing is really on risk assessment and initial management strategy. The consensus is very clear on one thing. If a man with localized prostate cancer is found to carry an inherited BRCA2 mutation, he should not be offered active surveillance.
Not offered it at all. That's a strong recommendation.
It is. Because the data shows that men with BRCA2 mutations tend to have more aggressive prostate cancer, it's more likely to spread, survival is shorter, and even if it looks low risk initially, it's more likely to be upgraded later if they're just watched. So finding that mutation really pushes towards definitive treatment up front, like surgery or radiation.
So a single gene finding can completely shift the plan for supposedly low-risk cancer.
Absolutely. For other localized patients without that specific high-risk mutation, there are also tissue-based genomic tests, things like Prolaris, Decipher, Oncotype DX that look at gene expression patterns in the tumor biopsy. These can give additional information about the tumor's aggressiveness, helping doctors and patients decide between active surveillance and immediate treatment, refining the risk assessment beyond just Gleason score and PSA.
But routine germline testing isn't for every man with localized prostate cancer yet.
No, not according to this consensus. It's recommended mainly if there are those red flags, the family history, the aggressive pathology features we discussed earlier.
Okay, what about when the cancer has spread but is still responding to hormone therapy? Metastatic hormone-sensitive prostate cancer, MHSPC.
In that setting, MHSPC, the genetic testing results currently seem to have less impact on choosing the first line of therapy. That decision is usually based on standard factors, hormone therapy, plus maybe chemo or a newer androgen receptor drug. But the consensus says the genetic info is still valuable for prognostic counseling, giving the patient a clearer picture of what to expect long term. And it's crucial for planning ahead, knowing what targeted options might be available down the line if or when the cancer becomes resistant.
So it's more about looking ahead in MHSPC, which brings us to MCRPC. Metastatic castration-resistant prostate cancer. This is where testing has the biggest treatment impact.
Absolutely, unequivocally yes. In MCRPC, genetic testing is now essential for guiding systemic therapy choices. The number one example is PARP inhibitors.
Like olaparib and rucaparib.
Exactly. These drugs specifically target cancer cells that have defects in homologous recombination repair, or HRR. So finding mutations in genes like BRCA1, BRCA2, ATM, PALB2, these HRR genes directly opens the door to using PRP inhibitors.
And the PFound trial was key here.
It was a landmark trial. It showed that olaparib worked significantly better than switching to another hormone therapy in MCRPC patients whose tumors had these HRR mutations. The benefit was especially strong for men with BRCA1 or BRCA2 mutations. So based on Profound and other studies, PRP inhibitors are now a standard consideration for MCRPC patients with qualifying HRR mutations, usually after they've progressed on initial hormone therapies and maybe chemotherapy.
Okay, PRP inhibitors for HRR mutations. What about the immunotherapy connection again? MSI high.
Right. For that, roughly 3% of MCRPC patients whose tumors are MSI high or dMMR, the immune checkpoint inhibitor pembrolizumab is a clear option thanks to that FDA approval. It might be a small percentage, but for those patients, it can be a very effective treatment.
And you mentioned platinum chemotherapy earlier, an older drug class.
Yeah, it's interesting. The consensus points to retrospective studies suggesting that platinum-based chemotherapy drugs like carboplatin or cisplatin might also be particularly effective in MCRPC patients who have HRR mutations, especially BRCA1 or 2. It's not based on huge randomized trials specifically in prostate cancer like the PRP inhibitor data, but it mirrors what's seen in BRCA-mutated breast and ovarian cancers, where platinum is known to work well. So it's another potential option guided by the genetics.
So, wow, in MCRPC, the genetic testing is directly unlocking doors to targeted therapies, PRP inhibitors, immunotherapy for some, maybe even guiding chemo choices. It really is changing how treatment is selected.
It absolutely is moving away from treating everyone the same and towards precision oncology.
It sounds fantastic, but what are the roadblocks? The practical challenges to getting this done for everyone who needs it?
Well, the consensus brings up several important ones. We talked about the technical side, choosing the right test, sample quality, detecting LGRs, using liquid biopsy effectively. But a huge bottleneck is genetic counseling.
Why is counseling so critical here?
Because finding an inherited mutation, a germline mutation, has implications way beyond the patient sitting in front of you. It impacts their children, their siblings, other relatives. They might share the same increased cancer risks. Genetic counselors are trained experts who can explain these complex results, what the risks mean for the family, what the options are for cascade testing relatives, and discuss surveillance or prevention strategies. It's a crucial piece.
But there aren't enough counselors.
That's the reality highlighted in the source, and it's a global issue. There's often a shortage of trained genetic counselors, leading to long waits or lack of access, creating a real unmet need. You can't just hand someone a complex genetic report without that expert support.
Make total sense. You need someone to translate the science into personal meaning.
Precisely. And the cascade testing itself, getting relatives tested, faces hurdles too. Prostate cancer maybe historically hasn't been thought of as strongly hereditary as breast or ovarian cancer, so families might not be primed for it. Also, for conditions like Lynch syndrome, prostate cancer isn't always the index cancer that triggers the family investigation. And the source even hints that maybe men, culturally or for other reasons, might sometimes be less inclined to pursue genetic testing than women.
Those are very real-world barriers. Okay, so summing up this genetics section, the consensus statement shows us genetic info is now fundamental. It's changing how we manage risk even before diagnosis for some, helping refine decisions in localized disease, and, most dramatically, guiding personalized therapies in advanced resistant cancer. It's personalized medicine in action.
It's moving us towards making treatment decisions based on the specific biology driving that individual's cancer. Less guesswork, more precision.
Right, so we've seen how genetics is applied clinically now. But to really get ahead of aggressive cancer, we need to understand its core survival tricks. Let's shift gears now, move from the clinic to the lab bench. Tell us about the research looking at the cell's inner workings.
Okay, so this next part focuses on two fundamental areas: how cancer cells get their energy, their metabolism, and this fascinating ability they have to actually change their identity to survive treatment.
Let's start with metabolism. The study you brought looked at something called oxidative phosphorylation, OXPHOS. I usually hear about the Warburg effect, cancer cells loving sugar and glycolysis. How does OXPHOS fit in?
That's a great point. The Warburg effect, or aerobic glycolysis, is definitely important for many cancers. But this research highlights that OXPHOS, the more efficient way cells make energy using oxygen in the mitochondria, can become really critical for certain types of aggressive cancer cells. Think cancer stem cells, or cells with specific mutations, or especially cells that have become resistant to therapies like hormone therapy. These resistant cells sometimes become highly dependent on OXPHOS.
So targeting OXPHOS could be a way to hit those resistant cells.
That's the idea. It's an attractive target because these aggressive cells seem to need it. But the big challenge is that our normal healthy cells also rely heavily on OXPHOS. So finding a way to inhibit it in cancer without causing too much damage to normal tissues is tricky. Potential toxicity is a major concern.
Okay, so this specific study looked at that interplay inhibiting OXPHOS while also considering the androgen receptor, AR, pathway, which is key in prostate cancer. They used different drugs and different cell lines.
Exactly. They use prostate cancer cell lines that represent different stages or types of the disease, and they hit them with two different OXPHOS inhibitors. One called oligomycin, which blocks the very last step, the ATP synthase enzyme.
It's the cell's main energy generator.
Right. And another drug, IACS 010759, which targets an earlier step, complex 1 of the electron transport chain. And crucially, they tested these drugs in conditions mimicking hormone therapy low testosterone to see how OXPHOS inhibition interacts with AR signaling suppression.
And what did they find? I imagine it wasn't simple.
Definitely not simple. The results were really interesting and very dependent on the specific cell line they were looking at.
Okay, let's break it down. What happened in VCAP cells? They're androgen sensitive, right?
Yes, VCAP-2 cells respond to androgens. When they grew these cells in low testosterone, mimicking castration, and treated them with oligomycin, the ATP synthase inhibitor, they saw massive cell death, apoptosis. Within 48 hours, look really promising.
Okay, great. Hit their energy source, they die.
But here's the twist. If they added back just a little bit of testosterone, enough to activate the AR pathway even slightly, it completely rescued the VCAP cells. They survived the oligomycin treatment.
Wait, adding testosterone saved them from the metabolic drug? How does that work?
It's a fascinating finding from this model. It strongly suggests that for oligomycin to be lethal in these VCAP cells, the AR pathway also needs to be shut down. If there's still some AR signaling happening, these cells somehow find a way to cope with the OXPHOS block. It points towards a potential synergy, maybe hitting both AR and OXPHOS together could be really powerful, but it also hints at a resistance mechanism. If AR isn't fully blocked, oligomycin alone might not be enough for these cells.
That really shows how tangled these pathways are. Okay, what about the other OXPHOS drug, IACS 010759, in VCAP cells?
This result was just as important, but kind of worrying. IACS 010759, the complex 1 inhibitor when used alone on GCAP cells, actually seemed to increase their viability, make them grow better.
Increased viability.
Yeah.
A drug targeting their energy production made them healthier.
In this specific cell line model, yes, and adding testosterone boosted this effect even further. This is a major cautionary flag. It suggests that inhibiting OXPHOS at complex 1 with this particular drug might actually have unintended pro-tumor effects in some prostate cancers.
Why would that happen?
It's complex, maybe it forces them onto other metabolic routes or triggers some survival signal. But the key takeaway is not all OXPHOS inhibitors are the same. You can't just assume blocking the pathway anywhere will be good. Specific targets matter, and some might even backfire. Needs careful investigation before thinking about clinical use.
Wow, that's a critical lesson. Specificity matters, and watch out for unintended consequences. What about other cell lines, like LNCCAP, also androgen sensitive?
LNKP cells were quite different from VCAP. They were highly sensitive to both oligomycin and IACS 010759. Both drugs caused a big drop in viability.
And did testosterone rescue them?
Not really. In LNTP, adding testosterone didn't seem to protect them much or at all from the OXPHOS inhibitors. So in this model, targeting OXPHOS seemed pretty effective regardless of the testosterone level.
Interesting. And they also used LNCAP C40B cells. Those are like LNCAP but resistant to low testosterone.
Exactly. They keep AR signaling active even in castration conditions, modeling that resistant state. And these C4-B cells were a bit less sensitive to oligomycin than the original LNCAP cells,
suggesting that persistent AR signaling gives some protection.
It seems like it might, at least against the ATP synthase inhibitor oligomycin. However, these resistant C4-B cells were still extremely sensitive to the complex 1 inhibitor IACS 010759, even with testosterone around.
So it's complicated. Sensitivity depends on the specific drug, the specific cell line, and its AR status.
It's a very complex interplay. Now, what about PC3 cells? These are AR negative, representing aggressive metastatic disease that doesn't rely on androgens. PC3 cells were the least bothered by either drug. They didn't see the massive cell death like in LNTP. Instead, the main effect was just slowing down their growth.
How did it slow them down?
It looked like changes in the cell cycle. More cells got stuck in the G0, G1 phase, the resting or preparation phase, and fewer were progressing through S phase, where DNA is copied, or G2M, the division phase. So it arrested their proliferation rather than killing them outright. And as you'd expect for AR-negative cells, testosterone had no impact.
And they compare this to normal cells too, HEK293.
Right, as a control. HUK293 cells, which are normal human kidney cells and AR negative, also showed reduced viability with the inhibitors. But again, it was mostly slowed growth and cell cycle changes, not widespread death. Testosterone didn't affect them either.
Why is that comparison important?
It highlights the core challenge with targeting OXPHOS. These inhibitors do affect normal cells, mainly by slowing them down. That's likely where side effects would come from in a patient. The hope is that the cancer cells are somehow more dependent on OXPHOS, creating a therapeutic window where you can hurt the cancer more than the normal tissue. But finding that window is key.
They looked at metabolites, too, like fuel molecules.
Yeah, some preliminary analysis. They mentioned seeing things like pyruvate levels dropping with oligomycin and VCAP, which makes sense if you block the end of OXPHOS. More intriguingly, they saw lactate levels increasing with the complex 1 inhibitor IACS 010759 in VCAP.
Increased lactate. I thought that was waste product from glycolysis.
Traditionally, yes, but there's growing understanding that cancer cells can be metabolically flexible. The source suggests this increased lactate might actually be taken back up by the cells and used as an alternative fuel source, feeding into the mitochondria downstream of the complex 1 block, a way to bypass the drug's effect.
Wow, so they can potentially use their own waste to survive the treatment. Clever.
Cancer cells are incredibly adaptable. It just shows how targeting metabolism requires understanding these complex feedback loops and alternative pathways.
Okay, so summing up this OXPHOS metabolism study, what are the big picture implications for aggressive prostate cancer?
Well, it really hammers home the complexity. The interaction between AR signaling and OXPHOS dependence is intricate and varies between different cancer subtypes or models. It suggests dual inhibition hitting AR and OXPHOS could be powerful, maybe synergistic. But it screams caution too, especially with that complex 1 inhibitor it result in VCAP. Not all OXPHOS drugs are equal. Some might even be harmful in certain contexts, and the effect isn't always killing the cells. Sometimes it's just slowing them down. So we need very selective, potent OXPHOS inhibitors and likely need to use them smartly, perhaps in combination therapies, to maximize benefit and minimize harm to normal cells.
It's clearly not a simple turn off the power strategy. It's much more nuanced. Okay, let's pivot to the other survival trick. Cellular plasticity. This is ability of cancer cells to change. The news item you found focused on work from the University of Michigan.
Right. This tackles a huge clinical problem, lineage plasticity. It's when prostate cancer cells, often under the pressure of hormone therapy, basically reprogram themselves. They change their fundamental characteristics, sometimes becoming like neuroendocrine cells or other types that are no longer dependent on the androgen receptor.
So they literally change who they are to escape the main treatment.
That's a perfect way to describe it. They undergo this transformation, this lineage switch. And this is a major reason why we get these really aggressive AR-independent forms of prostate cancer that are so hard to treat.
And this Michigan study identified a specific gene driving this.
Yes, they pinpointed a gene called PROX1 as a key early driver of this lineage plasticity process.
An early driver, like it flips the switch to start the transformation.
That seems to be the idea. Increased PROX1 activity appears to be one of the initiating events that pushes these cancer cells down that dangerous path towards becoming AR-independent and treatment-resistant.
Okay, so PROX1 is a bad actor here. But what makes this finding potentially actionable?
The really exciting part is the connection they found. PRX1 doesn't seem to work alone. It functionally collaborates with a family of enzymes called histone deacetylases, or HDAs.
HDACs, I've heard of those. There are drugs that target HDACs, aren't there?
Exactly. That's the crucial link. PROX1 itself might be a difficult protein to target directly with a drug, but HDACs, we already have several FDA-approved HDAC inhibitors for other types of cancer.
So the idea is if PROX1 needs HDACs to do its dirty work of driving plasticity,
then maybe using an HDAC inhibitor could block PRX1's function even if you're not hitting PRX1 directly. You target its essential partner.
it's that guilt by association strategy again. Go after the druggable accomplice.
Precisely. It provides a strong molecular rationale for testing these existing HDAC-AC inhibitors in patients with aggressive AR-independent prostate cancer where lineage plasticity, potentially driven by PROX1, is suspected.
That could open up a whole new treatment avenue for a group of patients who have very few options right now.
That's the hope. It's a potential way to target this fundamental resistance mechanism using drugs that are already available, although they'd need to be carefully tested in this specific context.
Now, the research sounds solid, based on patient samples and lab work.
Yeah, the publication mentioned using patient biopsies, genetic manipulation in cell models, sophisticated assays. It seems like rigorous basic and translational science pointing towards a testable clinical hypothesis, published in a good journal, Journal of Clinical Investigation.
Okay, so connecting this back for everyone listening, these lab studies are peeling back the layers on how aggressive cancer cells survive. The Oxfos work shows their metabolic flexibility, hinting at future strategies targeting energy pathways may be combined with other drugs. The PROX1 work reveals this shape-shifting ability, lineage plasticity, identifies a driver, and crucially, links it to existing drugs, HDAC inhibitors that might block it. This kind of fundamental research might seem distant from the clinic sometimes, but is absolutely essential for developing the next wave of treatments.
You have to understand the enemy's tactics down to the molecular level to figure out how to counter them effectively.
Right. So we've covered the genetics guiding treatment today, and these deep dives into the cellular mechanisms pointing towards tomorrow's therapies. Let's try to synthesize this. What does it all mean when we put it together? How do we fight this complex beast of aggressive prostate cancer?
Well, the first thing is acknowledging that aggression and resistance aren't caused by just one simple thing. It's multifaceted. You've got the underlying genetics, some inherited risks, plus mutations the tumor acquires along the way. The consensus statement showed us how we can use that genetic blueprint now to identify risk and target specific vulnerabilities, like with PRP inhibitors.
Okay, genetics is one piece.
Then you have the cell's internal machinery, how it fuels itself, its metabolism. The Oxfos studies show how complex that is, how it interacts with therapies like AR inhibition, and how resistant cells might rely on different energy pathways. That's another angle of attack, potentially.
Metabolism's piece two.
And then there's this remarkable adaptability, the plasticity. The PROX1 research highlights how cells can fundamentally change their identity to evade treatment. Understanding the drivers, like PROX1, and their partners, like HDACs, gives us another potential strategy blocking the transformation itself.
So genetics, metabolism, plasticity. It's like fighting on multiple fronts.
Exactly. And that's why we need different types of research. The clinical consensus gives us the practical roadmap based on current evidence how to use genetic testing effectively today. The lab studies are exploring the fundamental biology, uncovering the why behind resistance, and identifying new potential targets and strategies for the future, like hitting Oxfos or using HDAC inhibitors to block plasticity. Both are essential.
And it all points towards making treatment much more personalized, doesn't it?
Absolutely. That's the common thread. Moving away from treating all advanced prostate cancer the same way, genetic testing allows for personalization now based on mutations. The metabolism and plasticity research suggests future personalization could involve understanding a tumor's specific energy profile or its propensity to change lineage and tailoring treatment accordingly.
The goal is clear, but the challenges seem pretty significant too.
Oh, definitely. Getting widespread, equitable access to high-quality genetic testing and the crucial genetic counseling support is a huge challenge globally. And translating those exciting lab findings like selective Oxfos inhibitors or the best way to use HDAC inhibitors against plasticity into safe and effective treatments for patients is a long, expensive, and difficult road. Development pipelines are tough. Plus, cancer is always evolving. Even as we develop new therapies, the cancer cells will likely find new ways to resist. It's a constant arms race.
But the flip side is the opportunity, right? Finding new targets, maybe repurposing old drugs in new ways based on these discoveries, getting better at predicting who will benefit from which treatment.
The opportunities are immense. Every insight into the biology gives us a potential new angle. The goal is more effective, less toxic, truly tailored treatments that can turn aggressive prostate cancer into a manageable condition for more patients.
It's clearly a field moving at lightning speed.
It really is. The pace of discovery is remarkable.
Yeah. Okay, this has been a really rich discussion. We've seen how genetic testing is becoming standard practice, especially in advanced prostate cancer, steering treatments like PRP inhibitors and immunotherapy based on specific mutations. That's happening right now. And looking ahead, we've explored the lab research uncovering these fundamental survival mechanisms, the metabolic juggling acts shown in the Oxfos study, and the identity-changing plasticity driven by genes like PROX1, potentially targetable with HDC inhibitors.
It really highlights that progress comes from understanding the unique biology of each tumor, from the genes up to the cell's behavior.
So the fight against aggressive prostate cancer is being waged on all these levels. From the genome guiding today's therapies to the deep cellular mechanics revealing tomorrow's targets. It definitely leaves you thinking. With all this incredible science uncovering how cancer adapts and resists, how fast can we actually translate these discoveries into real-world benefits for patients? How quickly can we close that gap between the lab bench and the bedside, especially when the cancer itself is constantly moving the goalposts?
That translation gap, bridging it faster, is the critical challenge and the ultimate goal.
A crucial race indeed. Thanks for joining us for this deep dive.
Thanks for listening. For all things health and fitness, subscribe to our newsletter today. Find out more at ArmyGymnastics.com.